Hi everyone. This video is actually an enhancement on the previous video we had on edit distance. So approximate string matching is going to give you an algorithm which is going to use the edit distance algorithm to find the difference between two strings. So in edit distance we had a string of size m plus 1 comma n plus 1. So you see that this matrix is that big. The order complexity of that was order m cross n, and that makes sense because the matrix is that big and you're filling it up. In approximate string matching, what happens is you're also given another parameter, which is a threshold parameter, t. And what you need to do is you need to just answer a yes and a no between can the edit distance between these two strings be less than t. Okay, so if I take an example, let us say AA and BB, and let's assume that all costs are 1, 1, 1. So if I say that can the edit distance be with t equal to 2, can you convert this string to this string with cost equal to 2? Then the answer is going to be yes, because I can convert this A to a B and this A to a B and get this string which is equivalent. Similarly, if I say what happens with t equal to 1, then the answer is impossible. I cannot convert this string, I cannot convert AA to BB with this as my threshold value. So, of course, one way to do this is to entirely traverse the matrix, but that is dumb and therefore you won't do it. What you can do is also when you're traversing the matrix to find positions where the cost becomes greater than t. And at that point you can actually leave the matrix and try only those positions which are less than equal to t. But that is also not efficient enough. So what we are going to do is we are going to find some mathematical properties in this to bring down the complexity. Right, so now things are going to get a little involved, especially in math, so I'll need your full concentration. The first thing that is very easy to notice is that the edit distance dmn, which is stored over here at the end, is the edit distance between the two strings. So that has to be less than the threshold value. That is a given condition. The second thing to note is that this matrix can instead be converted into a graph. You can consider all of these points to be nodes, and the cost to get from here to here and here to here can be given through the dynamic programming function that we had in the previous lecture. Okay, so this will be a new node and so on and so forth, such that each node is connected with a weighted edge. Right, that edge weight is going to be the cost of addition or cost of deletion or cost of transition. So one thing that you can do is you just use Dijkstra's from here and you can go here. But the order complexity of that is even higher than the normal edit distance that we have. But I'm trying to think in terms of graphs now. Okay, if you're thinking in terms of graphs, think about the cost of a point d of x comma y to a point d of p comma q. When you're moving from this point to this point, what is the minimum distance that you'll have to traverse? So one thing that can happen is that you get all characters the same from xy to pq. All characters are the same and you're just heading along the diagonal. If you head along the diagonal, that's damn good because the cost can be 0. But if this line is not along the diagonal, so let us say the diagonals are put like this, and this line is slightly tilted, so it's not along the diagonal, it's moving a little away. What you can do is you can find the difference between this diagonal, which is starting over here, right? This point coincides with one diagonal, and this diagonal, which PQ coincides with, and you can take the difference between these 2 points, right? Where it should have been had it been cost 0 and where it actually is. Okay, so if that happens, then what's going to happen is that you'll have d of p comma q at least greater than or equal to d of x comma y plus, let us say, cost. So what I'm going to do is I'm going to take the minimum cost because it has to be greater than or equal to at least the minimum cost. So c of min, which is c min is nothing but minimum among ca, cd, ct. And you can intuitively understand that this is because you're making steps here, right? Each step is going to cost you something. So I'm taking the minimum step as the cost into the difference between the two diagonals. So that's going to be, p minus x minus q minus y. Okay. This is the diagonal at which, this is the difference in the diagonals in the y portion, and this is the difference in the diagonals in the x portion. Okay. The next thing to notice is that d of mn has to be greater than or equal to d of pq. And to understand this logically, have a look at d of pq. Why are we even seeing d of pq? We are trying to figure out whether this exists in the path from 0, 0 to m, n. That's what we want to do. We want to find out if pq exists in the path from 0 to 0 to mn, right? The shortest path possible. So, of course, if it exists in the path, then it has to be less than or equal to d of mn itself, which is the threshold. So, which is in turn lesser than the threshold. So, I can just replace this with a t. And what I'm getting here is that d of xy. To make things simple, I'll just give x and y the value 0, because that can be any point. So, this point can be this point also. So, giving this d of 0, 0, which converts this to 0 itself, because the first point is 0. X is 0, y is 0. We have p minus q. So, this turns out to be t is greater than equal to d of pq, which is greater than equal to c min into p minus q, right? And there's a mistake I made here, because if you just take p minus q, what could possibly happen is that p is less than q, all right? And if that happens, if p is less than q, so if the row number is small and the column number is large, then what you're supposed to do is you're supposed to take the modulo, right? Because we want to see the distance. Distance is a magnitude wise, so that's how you can explain this. So the difference between the diagonals, when you take from starting position to any point pq, which has to be going to the point mn, is giving you this equation. So what we have is t is greater than or equal to this quantity, which is c of min into p minus q mod, which gives us t is greater than or equal to, divide this by c of min mod p minus q, which in turn gives us t by c of min is, when you negate this, it becomes less than or equal to p minus q, and when it is positive, that time it is greater than or equal to p minus q. Okay, so what is this giving us? P minus q can be thought of as a diagonal, right? It's the diagonal where this point exists. So for this point to exist in the path from 0, 0 to mn, it has to be within the diagonal. I'm searching for a duster for a long time, yeah. So this is pq, and for it to be on the path to the final point, it has to be within these two diagonals. And what are those two diagonals? They are t upon c of min and minus t upon c of min, right? Those two diagonals which have x minus y giving them these two quantities. So what we have done is we have just reduced the time complexity of the overall equation. By instead of evaluating the whole matrix, we just evaluate the points which fall within these two diagonal points, within these two lines. Okay, but you can do even better. So the first thing I'll do is actually simplify this to call it t steps, right? Because that's exactly what it is. T divided by c min is the minimum number of steps that you're going. So t divided by c min is t steps. And can we do better? Yes, because I just replaced 0, 0 into xy. What you can do is you can also take it further. Take a point PQ again, right? What's happening here is that you can take PQ to be in the path from 0, 0 to Mn in two conditions. The first one, if it is existing from, if there's a path from PQ to Mn, then here's the thing, d of PQ plus the minimum cost, which we have said is t steps, or actually C min for us, into the difference between the two diagonals. So this is m minus n minus, or rather this is m minus p rather, and this is n minus q. Okay, this has to be less than or equal to d of mn, because this is the last point and that makes sense. So what we get is t, which is the threshold, has to be greater than or equal to d of pq plus c of min m minus p minus n minus q. Done. On the other hand, what we have is this path, which is d of pq itself, from 0, 0 to d of pq. So d of pq is greater than or equal to c of min into mod, I keep forgetting the mod, but remember that there's a modulo here and there's a modulo here. This is a multiplication into modulo p minus q. Okay, fine. So what's happening is this is greater than this quantity, which means t has to be greater than or equal to, because there's an addition here, c of min, I'll take that in common, mod of p minus q plus mod of m minus p minus n plus q. Okay, so again dividing it by this, I get t steps, and like I warned you, I have kept up to my promise of keeping this mathematically involved. Right, this is what we have, t steps. So at any given point p and q, we can check if this condition is satisfying t steps, right? It's easier actually when you're at that point to check for this condition, but if you want to find out the asymptotic complexity, what's going to happen is we'll need to analyze this. So when you're implementing, use this condition at any point pq, use the condition to find out if t steps is greater than or equal to this. All right, t steps is nothing but t by c min. So to simplify the analysis, what I'm going to do is I'm going to assume m minus n is some quantity x and p minus q is some quantity y. So this is the number of the diagonals that they have, right? And I'm always going to assume that m minus n is positive. The reason for that is because if not, then you can just switch the strings, and m minus n is always positive. So this is greater than 0. Okay, so there's just two conditions here. T of steps, this gives you t of steps is greater than or equal to mod y plus mod of x minus y. Okay, this is just because I put m minus n here and a minus p here. So this is minus of this, which is x minus y. So this leaves us with just two conditions. If y is positive, then t of steps is equal to y plus x minus y mod, with again two conditions. What if x is less than y, and what if x is greater than y? So if x is greater than y, then you have the condition t of steps equal to minus y cancel. You just have x remaining, which is, if you actually read into this, what's happening is x is m minus n, t of steps is t by c min. So if I multiply both quantities by c min, then this is just t. All right, and this is, I'm sorry, this is greater than or equal to. Okay, so is this condition of any use to us? And the answer is no, not at all, because this is the base condition, right? M minus n is the diagonal on which mn resides. What this is saying is okay, the difference between the diagonal between 0, 0 and mn has to be at most this, which is obvious because you're taking m minus n steps at least, and the cost, minimum cost, has to be less than or equal to this. All right, so this condition is useless. Let's just get rid of that. The second thing that can happen is x is actually less than y. So if that happens, then we have t of steps greater than or equal to y minus x plus y, in which case this is 2y minus x, right? Okay, let's keep it like this. The second thing that can happen is t of steps is greater than or equal to, now we are assuming that y is negative. So this is minus y plus, if y is negative, then this quantity is definitely positive. So we have already said x is positive, so positive plus positive is going to be positive, which is going to be x minus y. All right, x minus y has to be positive because y itself is negative, so it's a positive quantity plus a positive quantity. This entire thing is positive, that means, so you have x minus y. So this turns out to be t of steps is greater than or equal to x minus 2y. Okay, so can you see some interesting things here? This is the inverse of this, right? Just the signs have been changed. So let's multiply both sides by minus. What happens is this inequality was greater than or equal to, now it will become less than or equal to, and by shifting signs it becomes 2y minus x. Okay, so what you have is 2y minus x is less than or equal to t steps, and this is greater than or equal to t steps when negated. What is 2y minus x? 2y minus x is 2p minus 2q minus x gives us minus m plus n. Okay, now is x a constant for two strings? Yeah. So this turns out to be minus x. I'm sorry, this is plus x, because what we're doing is this minus x is now being added to both sides. So this is t of steps plus x less than or equal to plus x over here too, and this is what you have. Now divide both quantities by 2. I know this is getting really messed up, but this is just all this calculation is just so that we can find the complexity of this. When you're actually implementing, remember, you need to implement only this. Okay, so y is the diagonal you're at. Y, like we said, is p minus q, is equal to some constant and some constant, and between those two values. So p minus q, this diagonal has to be between these two values. All right, and writing that neatly, this will turn out to be minus t by c min plus m minus n, the whole thing divided by 2, right? This thing, I'm sorry, this is not minus t by c min, this is t by c min. So this quantity is actually this. All right, and to actually find this is a constant operation, of course. You know the threshold, you know c min, you know mn, you know 2. So this is going to be a constant, this is going to be a constant. Whenever you're at any point, you can check if that diagonal falls within these two constants. So what's effectively happened is that this diagonal has just gotten leaner, it's gotten thinner. Okay, and if you want to prove that it has gotten thinner, I'll leave that proof up to you. Basically, it's just 2t. Initially that you had 2t steps, and now it is, you need to multiply this by 2, right? So that is 2s plus x, which is m minus n. And t has to be less than m minus n, t steps. You can't take more than m minus n steps to get here. Okay, I hope you understood that. I'm sorry if this point became too mathematical, but there is no other choice. What you can do is you can actually just take the cases one by one and see that the math proof works out for yourself. Of course, implementation stops right here because you know that if P and Q are not satisfying this condition, you're done. Edit distance through this way with the threshold value, what you can do is you can actually approximate whether two strings are matching or not by throwing a particular threshold value. So if you had the complexity, of course, of m cross n, then with the threshold value, what's going to happen is you can see that this is almost like a rectangle of this width and height, which is going to be the minimum amongst m and n, right? Because if m is very small, then m comes in. And if n is very small, means columns are very small, then n is going to be taken in consideration. So overall time complexity, I'll just write it down over here to make it even more messy, is going to be T into minimum of m comma n. That's the overall time complexity. So if T is small, which is what it usually is, you can actually get this done. And so your approximate string matcher now is going to work like magic. So if you have any doubts or suggestions, you can leave them in the comments below. Do understand that this is a heavily mathematically involved proof. So if you have any issues, you can go through the links in the description, because that's written by Ukkonen. He's the one who discovered the algorithm, and he's a brilliant guy. He's been doing a lot on strings. If you like this video, then please press the like button. If you want further videos on string processing or other algorithms, you can click the subscribe button, and I'll see you next time. Q minus y, the whole square, right? It's silly why I'm doing this, but